Risk 5, increased influence. Does the world need another CPU architecture when that no longer reflects the typical workload? Perhaps not. It may need a bridge to get to it where it needs to be. The industry is increasingly talking about benefits brought up by the RISC-V architecture, but is it even the right starting point? While it may not be perfect, it may provide the flexibility necessary to move forward gradually. Computer architectures and software had followed by the first steps of the process developed 80 years ago. They aimed to solve sequential and scale arithmetic problems using a foundational technology that could solve any finite problems, provided had a sufficient memory. The chip industry has shown its reluctance to move away from that approach, particularly in industries that still run software developed 50 years ago. Software paradigms and backward compatibility have a huge influence. It took decades before programs migrated from a single processor to multiprocessor architectures in any meaningful way. And it doesn't until NVIDIA developed CUDA that applications targeting massively parallel processors started to be developed outside the highly specialized applications. So why the industry need another CPU architecture when a typical workload for many applications is data flow problem with a small amount of control? The answer lies in the many ways in which the RISC-V architecture can be evolved, and some of these may enable a slow migration rather than attempting to cross a wide chasm. A couple of weeks ago, a RISC-V community held its annual summit in Europe, showcasing the increasing manner in which RISC-V is being used and how its impact is increasing, particularly in application domains that do not have a lot of legacy software holding back. The RISC-V is no longer just the tiny embedded microcontroller that you are not even aware of that is in your product, said Sandro Gallo, CEO of RISC-V International. The RISC-V has entered a different phase. This is backed up by others. Compared to previous years in Europe, there was much more industrial attendance, says Larry Lapid, Executive Director of Business Development at Synopsys. The content was coming more than from industry, and that changed the tenor of the conference. What's seen is that RISC-V is starting to intrude in places that we didn't expect it goes even 5 years ago. Gallo provided several examples of significant progress. Infineon and they are adopting a RISC-V for automotive. Infineon said they are adopting a RISC-V for automotive, he said. The European Union is funding HPC project and funding automotive project. Meta is using it for AI in their accelerator cards. And NVIDIA estimated that last year, in 2024, they shipped 1 billion RISC-V cores in their CPUs. The others highlighted the significant advances of RISC-V in cutting-edge processors. It is not only the low end, but processor serving as a co-processor and accelerator for GPUs in certain segments, said Mohit Wani, Principal Product Manager at Synopsys. NVIDIA gave a presentation where they say they have almost 30 types of different kinds of functionalities across their portfolio, where RISC-V based cores are doing the jobs for those 30 plus functionalities. Some business and technical hurdles still must be overcome. Automotive is increasingly looking into RISC-V, said Ronald Janke. Design methodology head in a funnel offers IIS's engineering of adaptive system division. They have been hesitant because RISC-V is an open architecture. In the automotive industry, you always need someone to blame if something goes wrong. This is hard if you do not have a single provider, but a community. Today, they are increasingly looking into RISC-V to do the potential cost reduction, because in automotive, you look for every cent to lower the price. However, you need to have an ecosystem. It's not enough to have tools that are enabled to develop your processor, but also the software on top of that. RISC-V is gaining around, but it still has a way to go until we have RISC-V processors as the main horse in automotive area. Not everyone sees this as being highly noteworthy. However, RISC-V is not a solution for AI, not for training, not for inference, said Steve Lodi, Chief Marketing Officer at Quadri. RISC-V is simply just another control CPU in the same vein as the ARM x86, MIPS, Xtensa, and ARC processors. The latter two also provide the designer with the instruction set customization ability similar to and superior to that of RISC-V. As such, RISC-V offers nothing of technical nature that is lives and found better than its predecessors. So, to combine both extreme views requires a long-term understanding of the way that industry works. RISC-V has the ability to enable AI evolution, said Venki Narayanan, Senior Director for System Architecture and Embedded Solution in the FPGA division of Microchip Technology. It needs that. It's evolving. The models are evolving, both at the running and inferencing levels. It needs various data types, various memory elements, local memory, and to be able to do more custom coupling in a much faster way. If you look at that, there are various ways of doing it. RISC-V is enabling that with the domain-specific architectures. So, unique opportunity. It's rare in the chip industry that an application merges for which there is no legacy software. No, nevertheless, that is what happened with AI. Moreover, given the extreme rate at which the technology is evolving, no software is likely to become established before it is again disrupted. This creates the perfect environment for continuous evolution and adaptation. With no legacy software to support, you really can tell your processor to the workload and leave out things you don't need. That's not this rapidly. There's still a lot of optimization that can be done at the architectural level, even at a microarchitectural level, design pipelinings and caches and memory. And that's all before you get to anything else, before you get to the implementation. The freedom that comes with the RISC-V enables freedom in architecture. AI accelerator cards can have a huge number of RISC-V cores and even different cores with the same cluster, said RISC-V International Galileo. You can have 100 of little blocks, each of them different RISC-V cores, some dedicated to moving data in and out, and some dedicated to the inference itself and the processing. Then use the concept of the adding custom instruction that allows you to have a tensor units that are very efficient. This is how RISC-V is influencing the architecture of the chips. So the wild RISC-V licensing has a cost advantage that is not only region, it goes way beyond that, said Synopsys warning. If you look at the way accelerator connected to a processor, it is through a fast interface, and typically in a memory mapped fashion. From a developer perspective, if you want to work done on the accelerator, you send the data and the task information to the accelerator through the interface. Then you are waiting for the accelerator to send your result back. But that communication is expensive, and it means cores are sitting idle. You are wasting 30% of your time sending data and getting the result back, says Wani. You can avoid all of that time if you can natively do those particular operations, sending data through your own vector pipeline, which it then connects to the accelerator directory. This kind of flexibility only exists in the RISC-V world. The Quadric lobby is not convinced. All control CPUs suffer from the same severe limitation when applied to AI applications, particularly inferencing applications, he said. CPUs are designed to chase pointers in random code. They are not metric or tensor engines. At best, these CPUs offer vector multiply times vector computation throughput. They are bound by conventional load or store bandwidth bottlenecks. Thus, every approach supporting to use RISC-V for AI must bundle in a separate metric engine, which introduces graph partitioning problems that are Achilles heel of the CPU-based approaches. The appropriate innovation to tackle AI is the creation of the architectures that are inherent matrix times matrix or tensor times center optimize and break the CPU-centric dependency on memory caching and speculative out-of-order pipelines. So RISC-V enables pieces of this wrapped in a conventional control processor. So some of our members already have a custom tensor instruction, said Gallo. So that is flexibility of RISC-V. You can develop your custom instruction for your specific workloads, and then you carry the complete cost of ownership for your custom specific application. There is also value in standardizing and extending the specifications so that we share the cost of maintaining the compiler and the tool chains and the libraries. Where vector, we are working on metrics, and there will be different approaches to metrics depending on application use cases. If it is an accelerator card, if it is an AI IoT application or edge AI, there will be the different ways of implementing matrix acceleration. With other candidate on the horizon, you have to make do with what is available. Data flow is very important in AI and in many compute elements, said Microchip's Nalan Yanan. The compute requirements have grown and the needs to be in a more power-efficient way. It's not just the microarchitecture of the instruction. Microarchitecture of the instruction, fetch, execute, and the write back. It's how you organize the microarchitecture and the data flow. How do you get data in and out, particularly large amount of the data going from one layer to another way? You can't keep going and write back to DDR. As with AI evolving so rapidly, there need to be a lot of flexibility. The types of models that one needs to implement in an efficient manner are growing, said Nilam Lupaleria, segment reader for AI and communication and microchip. The transformers are what ChatGPT needs, And this is what made AI popular. But there are a whole set of models that are a lot less complex than a transformer. Those also need higher performance. For example, classic CNN, RNN, LSTM, they are the math block architecture. The DSP block architecture to be more amenable to those transformers or those models in order to make performance a lot better. So AI is not just one problem, and flexibility remains important. AI has multiple layers, said Narayanan. So you have segmentation, object detection, classification, transformers, and all of those use different data types. How are these layers being implemented? How can you do that efficiently? And how do you get the data in and out between the layers? Those are the questions that you have. This is how the architecture helps you build that. So it includes not only the operation, but the data. RISC-V has an inherent advantage where you can make custom hardware without violating the ISA specification, said Microchip's Ruparelia. You can make processing for specific data types better, be it at the instruction level, be it in with the microarchitecture, so you are building a custom computing solution for that class of workloads. This flexibility plays a big role in being agile towards the new data types as they come along. They will be coming along in the near future for different classes of applications. But the full requirement for a processor to optimize the task of tomorrow remains unknown. If we are building a processor for edge inferencing, it may doing classification, detection, segmentation, or even some sort of transformer, said Narayanan. These are fixed layers, and we know the compute elements are designed to be more optimized and work through these workflows. So we build a computer optimized for needs of the today. But that doesn't mean that if you have a new layer or a new operator types or something like that, we can do it. It's just that it's not going to as efficient as if you design it that way. Ecosystem. The ecosystem has been a major obstacle for adoption in application areas, but steady progress is being made. We upgraded our membership in the Yocto project in the platinum level, said Gallo. This is a strong message to the ecosystem. Yocto is the most pervasive embedded Linux distribution, so this is the first time in many years that a Yocto project added a new ISA, a new architecture, and being a platinum member means that a RISC-V will be on a par with the other architectures. So the Yocto is used not only for embedded Linux, Edge AI, IoT, but also consumer set-top box TVs, and automotive and the infotainment side. Mobile is catching up. Google has made RISC-V a first-class citizen as far as Android developed is concerned, says Wani. So, as the software stack matures, we will also see entry-level application cores and popular segments like mobile, laptops, and so forth. When enough leaders step in, the pack follows. Reddit announced that they have a developer preview of ARIA for RISC-V, says Gallo. Fedora is available for RISC-V last January. At FOSDEM in Europe, Canonical discloses that they are building plans to support the RV823 profile with Ubuntu. This message is that RISC-V is ready for application processor for standard operating systems. So significant investments are being made. Another interesting project is in Europe is the DARE project, said Rapidus. This is injecting the 260 million to 280 million euros over the next 5 years. The three key vendors are each building chiplets, not just the processor IP. One is a general purpose CPU, one is a vector accelerator, and one is an AI accelerator. Those chiplets will be integrated. RISC-V with a new chiplet architecture is interesting. The conclusion. RISC-V may not be the perfect solution for many applications, especially those related to the AI, but it could provide an evolutionary path. In addition, there is nothing else on the horizon that can provide a better alternative. Very few revolutions have succeeded in the semiconductor industry by having an open and growing community of people who rapidly evolve that definition of what they need today, what they think they might need tomorrow, and with a view to the horizon. They may be able to get where they ultimately need to be without taking on too much risk. By taking small steps, the economy can keep up and steady progress is made. Okay, the next one is China claims to have developed the world's first AI-designed processor LLM turned performance request into CPU architecture. The Chimeng is a new open-source project for full-stack chip design. China's leading scientific institution has taken the reps of the Chimeng, an AI-powered system designed to accelerate chip design. The new source project from the Chinese Academy of Sciences, CAS, uses LLMs for fully automated hardware and software design, and can be used to design entire CPUs, but sample chip so far seems rather puny. The Chimeng means enlightenment, according to an SCCM report on its unveiling. As of now, the two processors have been created using Chimeng CPU version 1, which is comparable to an Intel 486, and Chimeng CPU version 2, which is claimed to arrive on an ARM Cortex A53. At the time of this writing, CAS's link to the Chimeng CPU version 2 project details is broken. Chimeng CPU V1 version 1, despite our snark about the first design being i486 1989 level, there is significant advance from version 2 and version 1 to version 1 to version 2. Version 1 to version 2, if the new sample reaches 53 2012 capabilities. That's a 23 real RIP. We have previously written about the innovation in AI chip design software from Western companies like Cadence or Software. Both these names in the EDA field have widely adopted AI. Cadence, for example, has delivered multiple AI platforms across the key steps of design and verification. Meanwhile, we know that Softsystems DSO.ai has assisted with over 200 taped-out chip designs at the latest count. However, the appeal of the Chimeng at least as far as we can tell from this early PR, is that it could be a bold industry disrupt with wider applications. The SCMP notes that this open source effort had three key interconnected layers melding LLM chip design smarts, a hardware and software design agent, and various chip design applications. During test, it claims that a human can do it days what takes human teams weeks to achieve. So the U.S. sanctions force China innovation again. Human has come into view in the shadow of U.S. pressure on the technology sanctions in general. However, it seems even more timely in the context of the more recent moves by the U.S. Commerce Department with regard to the export control on software. Early this month, we report that China tech giants like Lenovo and Xiaomi were ruling after Washington cracked down on software license available from the likes of Cadence and Synopsys. As noted at the CSA researchers, China must react. As chip design tech is a strategically vital industry, so we await the Chimon CPU version 3 with V3 with great interest, but aren't expecting another 23-year leap in the technology stakes. That would be 2035 technology. Okay, next one is quite old one, not old one. The industrialized market showing signs of revival. ADI called a cyclical recovery in the chip market as demand returns. Against a backdrop of global trade volatility, our performance reflected the ongoing cyclical recovery, said ADI CEO Vincent Roche Pictures at the company's result call. The ADI forecast current quarter revenue at $2.75 billion, higher than market expectation and in line with a similar better than expected current quarter forecast from T1 to ST, from a TINST. The VC Q1 has a bottom, said the ST CEO John Mark Cherry at the ST Q1 resulting meeting. All of our markets grew sequentially with the expectation of a seasonal decline in the personal electronics, said the TI in its Q1 earnings report. The TI CEO Habib Ilan pointed to more and more evidence and signals that across all channels, all geographies, a recovery of the industrial market share. ADI also cited increased demand from automotive, but said it could have been affected by customers pulling in order to avoid tariffs. We think our order results were aided by the pulling activity, said an executive who estimated the pulling upside for auto orders to be in the high single digits. While growth in memory and advanced logic is guaranteed, the wider chip market has been stagnating, and positive forecasts from these companies are a sign of revival of demand from industry sector and some increase in orders from auto. Okay, next one is ASUS sees TSMC as a clear favorite for 2nm, but Samsung remains in the game. The inner published in Korea Tech Medium Joseon Biz, AMD's senior vice president, took a clear stance on the company's future manufacturing strategy. From the AMD's perspective, TSMC is currently the undisputed leader in the 2nm process technology. This means that a Taiwanese connect manufacturer is once again the preferred partner in the current technology round, at least at least as far as AMD's upcoming server processor are concerned. Gen 6 to N2, EPYC vanished as technical carriers. A few weeks ago, AMD announced that it would be the first customer to use TSMC's 2nm process N2. It is now clear that this is the next generation of EPYC server processors, codenamed Venice. These are based on the new Gen 6 architecture and will be officially launched in the market 2026. So they are currently being developed and manufactured in close cooperation with the TSMC and, according to AMD, and will focus on efficiency per watt and maximum performance. With the perspective note, a small side note that is nonetheless not insignificant. Lisa Su, CEO of AMD, visited the TSMC plant in Arizona especially to accompany this milestone in a media effective manner. Whether this was simply closing of ranks or a tactical signal to a potential second suppliers remained to be seen. Features and segment shift. The development of the data center segment was also discussed in the same brief. According to AMD's SVP, the company recorded growth of 57% in this area in the first quarter of 2025. These figures underpin the focus on the scale of a server and solution, which is reflected in the broader product range, among other things. With the EPYC 4005 series Grotto, the company now wants to make a greater inroad into the mid-range and low-end segment, an area that has previously been rather neglected. Leaks about technical data of the Gen 6 family are particularly interesting here. Up to 8 CCDs core complex dies, 96 classic cores and 256 so-called dense cores are being discussed, flanked by the 128 MB L3 cache per CCD. It remains to be seen whether this represented the final expansion stage or whether the AMD is once again pursuing a variant strategy here, as we know it from the Ryzen and Instinction divisions. So no exclusivity, something remains in discussion. Despite a clear preference for TSMC, AMD leaving it open as to whether the other foundry partners could also come into play. Samsung is mentioned as a possible second supplier. According to the AMD manager, the company is always in talks with suppliers who can offer the best service for our customers. There is therefore no exclusive partnership with TSMC, at least not on paper. Samsung Foundry and repeatedly committed to progress toward 2nm and underlying nodes, for example, SF2 and SF1.4 in recent months. Even if the design wins have so far been in short supply, particularly in the server segment where validation cycles are long and the risk of version is high. An actual switch from the AMD to Samsung will probably only take place if the technical and economic pressure is correspondingly high, for example, due to the supply bottlenecks or geopolitical consideration. Okay, thank you for today. Thank you for your time. I'll see you next time.